we challenge the droplet microscope. Question 2.
Question 2. Droplet microscope. So, problem number 2, droplet microscope.
without pH 12. And the topic I'm going to present today is problem number 2, the microscope. And here's the outline of my presentation. And here's the problem statement. By looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system. Investigate the magnification and the resolution of such a lens. And here are two of our main focus. First is the relation between the radius of the droplets and the magnification. And the second is the relation between the radius of droplets and the focal length. And here's our experimental setup and equipment. In our experiment, we start recording and we drop the droplet by a pipette. We use a pipette because pipette is more accurate. And we get the experimental data at the time that we move the pipette away in order to avoid the evaporation. And when we get the experimental data, we'll observe it to make sure that it's a shape in circle like this. If it's an elliptic or not a circle shape, we'll delete the data and do it again. And for each of our experiments, we'll do it 5 times and get the average data. And here's a demonstration picture. And the lens here is a pixel in order to calculate the magnification of our experimental data. And here's a phenomenon explanation. When we drop a droplet on the glass, the droplet will stay on the glass is because there's a pressure. And we use the place pressure equation to calculate the value of A and B. We have the mu of the water, and we get a G, and we get the R, which is 7.85. And so we can get the data of A and B, and we put it into an elliptic equation to make sure that to get the shape of the droplet. Oh, there's a surface tension of the water. And for focal length, we get the value of A and B, so we will get the radius of the curvature. So when we get a radius of curvature, we put it in the lens contrast equation for the thickness. And for the definition of a thickness and the thickness is we see that if here is a space. If this space is too small that we can't observe it, then we're sending it as a thickness. And in our experiment, we didn't see the parts of R2, so we didn't calculate R2. And here's a reference. And we drop the droplet on the glass, and which the foam is flat. So the R2 is close to infinity. So we can get, and the N represents the refractive index of water, which is 4 divided by 3. So we can know that if the focal length is bigger, the radius of the curvature will be bigger. And here's the definition of the magnification. We can calculate the magnification by this formula. And we can put the focal length in this formula. And we translate it into that formula. And SI is the image distance, and SO is the object distance. And for SI1 and SI2, 1 is a part of both here, and 2 is part down here, which means the spring. And in our experiment, we assume that when the light went through the foam, it has been fixed by themselves. So we neglect the F2, so we can get that formula. And the resolution, we know that there are two ways to calculate the resolution, but we choose this way instead of the pixel, because we think that to calculate the numerical aperture is more accurate. And the N here is the refractive index of the water, which is 4 divided by 3. And the A is the radius of our droplets. And here comes our experiment. For experiment 1, the independent variable is the volume of the droplet. And the dependent variable is the length of A and B. So our hypothesis is that the volume of the water will affect the curvature, the radius of curvature, which we get when we get A and B, so we can calculate the radius of the curvature. And in this fourth picture, we have different volume of the water, and we enlarge it in preparation. And with the same height, almost the same height, we can see that when the amount of the water increase, the radius of the droplet increase. And here's the relation between the A and B. And A is the radius of the droplet, and B is the height of the droplet. And the blue dot is the theoretical data. For theoretical data, we put A from 0.1 to 3.9. So we can get B, and we get a theoretical data. So we can see that our experimental data and theoretical data is almost beat. And when we get the data of A and B, so we can get the radius of the curvature. And we have the chart here. So we can see that the radius of the curvature is positively correlated with the volume of the water. And our experiment 2 is the volume of the droplet. It's also the same as experiment 1. But the dependent variable is the amount of pixels in the middle. In order to get the magnification, we need to observe the pixel in the middle of the droplet. We only observed the pixels in the middle of the droplet because there are some diffraction on the side of the droplets. And our hypothesis is that when the volume of the water is negatively correlated with the magnification and positively correlated with the focal length. And here's the relation between the amount of the water and the focal length, and the amount of the water and magnification. And here is the discussion of the volume of the water and the focal length. It's about the focal length. Because we know that the focal length, when focal length is bigger, the radius of the curvature will be bigger. So the trend of the curvature here has dropped. So here has a very flat here. You can see that it's a little bit related. And for the second discussion is about the magnification. In the theory that we talk about for here. And we know that the volume of the water, when the volume of the water increases, the radius of the curvature increases, and which means the focal length increases. So when the focal length increases, this value will be, if the focal length increases, this value will be smaller. So it's almost close to 0. So this one will be close to 0. But in our experiment, we can see that it's close to 1.5. We think that it will be smaller at the more value of the water. But if we have the more value of the water, the shape of our droplet won't be stable. It's hard to make it a circle. So we didn't do the experiment. And we put the theoretical data and the experimental data together. And the blue line is the theoretical data, and the red dot is the experimental data. And here's both the focal length and magnification. And the definition of our droplet is that we assume that for a droplet, that there's 2 circles for the droplet. So when we have less water, the 2 circles will be more near. So the middle that we observe will we'll get more about the circle part. But if we have more value of the water, the part in the middle won't touch the circle part. So we put the circle the sphere model in a comparison too. So we can see that if our experimental data is smaller than about 25 to 30, it will more like a sphere model. And if it's more than about 25 to 30, it will more like an elliptic model and same as the magnification and the focal length. And for experiment 3, we have different volume of the droplet. And the dependent variable is the resolution, which we can get from the angle. And the volume of the water, and our hypothesis is that the volume of the water is negatively correlated with the resolution. And we can also see that when the volume of the water is smaller than about 25 to 30, it will more like a sphere model. And if more than 25 to 30, it will more like an elliptic form. So here comes our conclusion. If it's below 25 to 30, it will be more like a sphere model. And if it's above 25 to 30, it will more like an elliptic model. And we can know that from this one, it's more easy to understand. When the volume of the water increase, the curvature will increase, the focal length will increase, and magnification will decrease, and resolution will increase. Thank you.
Question for the comment.
So how do you make the shape of, how do you control the shape of the droplet?
We can control the shape of droplets, so when we observe our experimental data, if the shape isn't the same, we'll delete it.
I mean, how do you control your shape of droplet? What device is used? What kind of?
You mean a pipette?
You use pipette, but you see the contact angle is over 90. Below 90 is very high. The contact angle is very high. And why is that? Can you explain why the contact angle is very high?
Why the contact angle is very
Yeah.
high?
Do you measure the contact angle?
We didn't measure them.
Oh, so you didn't measure. How do you measure the magnification, or you just use the formula?
We have pixel. We have the pixel on our phone, and we drop the droplets, and we see an image, the pixel of image, and by our formula.
Compare the iPad without magnification and with okay. So did you consider the spherical aberrations?
If it's smaller than 25 to 30, we consider it.
You consider. So you didn't consider what you do.
We did consider it if it's smaller than 25 to 30 of the water.
And in your experiment, you say the curvature can be used as b squared divided by 8. What is that?
It's an equation of
Yeah.
curvature. It's an equation to calculate the radius of curvature.
Oh, so you mean the whole droplet are the same curvature?
This one and this one. I'm sorry, I forgot to explain.
Oh, so you only calculate the middle point?
Yes.
Okay, can I start?
I'm going to opponent their team. My name is Alex. And the task is droplet microscope by looking through a single water drop placed on a glass surface, and you can magnify the object. So the structure of solving the problem, they first find they observe the phenomenon. They find the formula of the math formula to describe the shape of the droplet. Then use their experiment to prove the theory. Then the form of the theory they use the Fick's equation and Lensmaker's equation. Then the parameter, they change the volume of the droplet, only change. And so the strength, they are good at relevant modeling of the theory. They actually did that is a good model and easy to know. And they use graph to explain the theory. But I have some suggestions, and they can consider of the gravity and not parameters. Then we have volume and experiment data quite different to the theory data. And independent variable even change in different experiments. And I'm going to discuss about point with and of light, some physical operations, how to describe the droplet gravitation and curvature. So I invite there are 19 questions that I can pitch that to. Could you please tell me why the fluidity won't increase but decrease? Give that explanation.
It's the radius of the curvature. It's from a combination arcs term. We think that it's maybe the volume of water increase, so I can't be sure about why does it drop.
So maybe your device is problem, or something?
I don't think that we have the experimental error because we found that this data drops, so we do this experiment again and again, but we found even though we do it maybe 20 times, it's always drop.
Yeah, so why the 30 decreased? Any explanation? Because that's pretty weird, because after 30, the 35 also increased. So if the 30 is at the line that all increased, it's more like acceptable for me. But the 30 also actually decreased. Then in 35 increased. So I'm very so yeah, the next question. Okay, this is
I can explain it. I think that maybe it's because that I have said that when it's more than 25 to 30, the shape will become ellipsis. So this will drop. The shape model isn't the same.
the shape model isn't the same. So this is the experiment or the real life.
This is the experimental.
So, but that is just your theory, that won't affect the experiment. So maybe it will change, but only in the experiment theory line. Next, you mentioned that at 25 to 30 μL, the gravity below it, the gravity won't affect. Why? Why is that the number? Why 25 to 30?
The gravity won't affect?
Yeah, you're a droplet. Previous I asked you a question about to consider that gravity will affect the droplet, and you replied that at 25 to 30 it won't affect.
Because we think that the gravity will only affect the shape of the droplet.
But it also affects the curvature of the droplet, right?
If the shape changes, the curvature, the radius of the curvature will change, of course.
So you mean the radius change, so the gravity won't affect the curvature?
No, I mean the gravity will affect the shape of the model of our droplet. And if the shape of our droplet change, the radius of the curvature will change.
Oh, whatever. And how do you define focal length?
It's the part that we can see the pixel in the middle.
Focal length. I mean, the focal point. How do you define the focal point?
In our experimental data, we'll first get the magnification and we put it back into focal length by this formula. We get the magnification, so we can get a focal length, and we have the object distance, so we can get a focal length.
But how do you define your object distance? Since you didn't consider the convex index, you didn't consider the screen. Do you consider the screen? The index of refraction, do you consider the screen?
The object of distance is the thickness of our screen.
Yeah.
We neglect the F2 is because of we think that when the light go through our screen, the phone already fix it, or else when you look at the phone, it won't be so good.
But actually, do you know that the definition of the object distance is not the screen thickness?
I mean that we have.
And that is not the object distance, right?
Right.
Okay. And hold on. And in your experiment, you use a lot of pixel, right? You can see how much pixel, and you say you take the point, the middle point of the droplet. Then how do you measure the magnification of the pixel? You take average or only analyze the middle one?
We take. You mean? Oh, we only take the middle one.
Okay. And can you just there's a page that you describe your shape of the droplet as the two circle. Yeah, that one. So why do I use two circle to describe it? Yeah.
We seen this picture in a reference because we first do our experiment and we found that in our experimental data, if we only compare it with the LSS model, this part won't fit our theory.
Yeah.
So we go see another reference, and we found this reference that say we can assume that the droplet is combined by two circle and a curve.
Yeah.
And so we put this into our theory. We put this into our theory to do a comparison, and we found that it fits our experiment.
And did you? Next question. Do you do the experiment of the resolution?
We did. Yeah.
And to have picture, how do you just
Get the number.
how do you experiment it? The resolution.
We put the focal length and put data into this equation and the n, which is the refractive index of water.
Oh, so that is a prediction, right? Now you didn't do the experiment to real life experiment.
I mean that we put our experimental focal length and we put our experimental data into this equation.
Then how did you get your experimental data? What kind of method did you get your data?
For A, we put it in the tracker and we found the length of our A. Then we put the picture into tracker so we can find the data in the A.
But the definition of the resolution is that how small you can see the two lengths. They will close together and become one length. So do you do this experiment instead of you just measure the thickness or the theta? Yeah, you just measure the theta and the length of the lengths.
Because we saw this in this reference, and we found that when the resolution increased, the numerical aperture will increase. So which means that we have the relation.
Oh, you didn't do the first. Have you considered the wavelength of light?
No.
No. So the different wavelength of light, the water refraction rate is actually different. So I think in your report, you should consider the wavelength of light. It can make it more perfect.
We found that there is some diffraction on the side of the droplets.
No, I mean the resolution.
Resolution.
In your resolution, actually the wavelength of light actually will affect the resolution.
But the data that we choose is at the middle of the droplet.
Yeah.
And in our experiment, we found that if the wavelengths affect, which means that the diffraction happens, it will only happen at the side of the droplets. It won't affect at the middle in our experiment. So we take the data of the center of the droplets.
Do you think the wavelength of light will affect the magnification?
I think that it will affect the magnification if we take the data of whole droplets.
Then how the wavelength of light affect? How will it affect? Do you think?
I think. Wait. We didn't do the experiment, so it will affect the refractive index of the water. And which means the resolution will change.
How change?
How change? If I think I can't say surely, but I think if the wavelength is bigger, the revolution maybe will be bigger.
Okay, next question. Do you consider the temperature in your experiment?
We didn't consider temperature.
That's
We only control the temperature of our when we're doing experiments about 25 degrees.
yeah. And what about the humidity? Do you control it?
We didn't we can't control the humidity.
And that's your droplet actually. They will.
Evaporate.
Yeah. That's what I mean.
Okay.
And
When we're doing experiments, we first record and we drop the droplet by pipette and we remove the pipette and we get the data that when we move the pipette at the time that immediately that we move the pipette. So we think that in this very short time, the evaporation won't happen just so quickly and to affect our experimental data.
done.
Okay, so please summarize the discussion.
Oh, okay. So I asked a few questions about your experiment. First, I asked, do you consider gravity? And they replied. I asked why the 30 mu decreased. They replied that because the formula to describe the shape of droplet changed, so it will decrease. And then I asked, how did you define the object distance? They replied that the thickness of the iPad. And I asked, how do you know the curvature of the drop? And they say they take the middle point of the droplet. Then I asked, how do you measure the magnification? And they replied they take the middle one to analyze it. And then I asked the wavelength of light, it affect this experiment, and they said they didn't consider the wavelength of light. Then I asked,
Okay, time is up. So for the review, please take your question.
So firstly, I want to ask for both of you. The droplet is a square shape or something else. Will it affect the phenomenon?
the first shape, is that?
The shape of the droplet.
It's
It is a square or something else.
actually a spherical, but in her experiment, they consider that is a ball. And
I did talk about the vertical. I talked about the horizontal. If the droplet is like a square shape, how will it affect?
square shape.
Yeah.
Oh, Oh, it's an interesting question because the radius of the droplet actually changed. You mean?
So how will it affect the phenomenon?
I think it will affect the curvature on the top of it. But she only takes the middle magnification, so I think the effect is numerous.
Okay, how about the report?
I think that it will affect our magnification, and also if it affects our magnification, also means that affect our focal.
Okay, thank you. So both of you, what will decide the image whether it is virtual or real?
It's virtual.
Okay, how about you? Virtual. So the reviewer thinks that when the object distance is larger than the focal length, it will be a real image. Thank you. And how will surface tension affect the phenomenon?
The surface tension actually affects the contact angle, and the contact angle is proportional to the average curvature.
And I agree with you. The surface tension will affect the shape of our.
Okay, thank you. So what is the difference condition of different kind of aberration? Since you mentioned the spherical aberration.
Spherical aberrations. If there are spherical aberrations, you should delete them because the focal length are different, right? So that is not the one that we shouldn't do in our experiment. We shouldn't take those data.
Okay, but you mentioned that the droplet is a sphere, so you need to consider the spherical aberration.
But in your magnification, you don't take the middle one. So in the curvature, you don't have to take the outside because the spherical aberrations are too affect too many problems. It equals too many problems, so you have to delete it off.
But we could have the equation to solve that part. So can you directly explain how will the phenomenon change if the camera is not vertical to the droplet?
Yeah, you have to place the vertical. Yeah, that is the magnification will be bigger.
Oh, thank you. So for the reporter, can you give some extra parameters that will affect the phenomenon?
We think that maybe.
Thank you. notice the rate of control, the shape of the droplets, and discuss about the deviations for some points, and notice the weird part about the resolution analyzing method. However, he didn't discuss the angle of the view, and didn't discuss about the surface tension, and he didn't notice that the error bars are strict. And also, they didn't discuss from the form of the image and the spherical operation. For the case discussion, the opponent asked for the wavelength of the light. Asked for how you consider the wavelength of the light. The reporter answered for none. And the reviewer thinks that the wavelength will affect the refraction, but that is small changes in the wavelength. And the key discussion 2 is the object distance. The opponent asked for how to define the object distance. The reporter said that the object distance is the thickness of the iPad. However, the reviewer thinks that if you use thickness of the iPad as your object distance, there will be some deviations. So we should follow the current statement to place a glass surface and something else down below it. And for our question, is a spherical operation. I asked for the opponent to how will the spherical operation affect the phenomenon. However, the opponent said that they didn't take it into account. However, the reviewer thinks that spherical operation is the main cause of the differences of the magnification. And I asked for the image form. The reporter and opponent both answer for the virtual, but it will change depends on the object distance. And for the point base, the reporter didn't mention a spherical operation in her report. And take of parameters which are the intensity of the light, the refractive index of the glass in the water, and the radius of the droplets. And they didn't discuss the definition of the magnification. And they did discuss a lot of measuring methods and the shape control of the droplets. And did discuss the definition of the resolution well. Thank you.
So concluding remark from the reporter.
Thanks for the opponent and the reviewer. And here's the concluding remarks. First, for this board is the conclusion of our experiment. The radius of curvature is positively correlated to the volume of the droplet and is also positively correlated to the focal length, and is negatively correlated with the magnification. And the experimental data closer to sphere model for lower volumes and close to elastic model for larger volumes. And we think that gravity only affects the shape of droplets, and then the radius of the curvature will also change, which means if the radius of the curvature changes, the focal length and the radius of the focal length will also change. And we measure the pixels only in the middle, where the diffraction does not affect. And the wavelength can be taken into consideration. But we think that in our experimental data, it won't affect a lot. And we minimize the effect of evaporation. And we should take other potential factors into consideration, like the type of our liquid. If we change the type of our liquid, the reflective index will change, and also the viscosity will change. So maybe we should do more experiment about different kinds of liquid. Thank you.
So it's time for the tutor to answer the question.
So, first question for the reporter. You think evaporation is not good for the experiment?
I think that if it happens, we need to fix this error. If
You think that's an error? But, I mean, if you drop a droplet, it evaporates, so it becomes smaller. Could you observe that? So you change the size of the lens.
the radius and the height will change, which means that the radius and the relation between the radius and height and the curvature and the focal length is correct, but the amount of water maybe will not be correct. because when it evaporates, the amount of water will decrease.
That also change the size of your lens, right? I think that is an advantage rather than a disadvantage. Anyway, so I have a question for opponent and reviewer. You think two of you do not agree with the reporter's definition of the resolution. Then why is the correct definition of resolution?
I go first.
For opponent.
I think the resolution you have to consider the wavelength of light, because wavelength of light is the basic parameters of the resolution. So she didn't do the resolution. I think she should improve it.
I agree with the wavelength, but also I think the definition of a resolution should be used the light per millimeters to make sure we can observe the two different lines here, which will, because of the resolution will be changed due to the magnification. So we should investigate the light here, which will affect by the magnification more to consider the resolution.
I always expect your answer. What determines the curvature of all of it?
Divide
What determines the curvature?
and the water amount and the contact angle.
The shape of the droplets.
The shape of the droplet and the contact angle.
Yes.
So, let me follow the first picture. So, what's the relation of magnification and resolution, and how you define the experimentally the resolution? Interestingly,
Of the resolution.
yeah, resolution.
In our experiment, we have tried to use pixels to count our magnification and the resolution. But we think that we use one data to calculate two things, two parameters. So we found another accurate way to that numerous aperture to calculate the resolution.
I think there are positive coloring, the resolution and magnification.
Can I use the whiteboard? In this formula, we can see that So we can see that the lens, the resolution of the lens depends on the resolution of the camera, which we use to shot the photo of the condition of the magnification, and times the magnification and the Epson of the light pair per millimeter. And the light pair per millimeter is like, this was two lines. And the smallest light pair condition is two line shows in the same condition. And so that the resolution will be smaller. Thank you.
The time for the score. So the score for the reporter. 6. The score for the opponent 8, 7, 7, 6, 7. The score for the reviewer 9, 9, 8, 8, 8. I think that's one answer. So let's close this session.